Good morning to one and all. This is Dr. Amar, Principal of West Godavari Institute of Science and Engineering. Uh, Today, I would like to tell you about quantum machine learning. First of all, I would like to thank our research uh, Dr. Bachu Srinivas sir for giving this wonderful opportunity. And I would like to thank all the organizers from Siddhartha uh, Institute of Technology and Sciences, UGC Autonomous, and Department of EC, and special thanks to uh, Dr. Bachu Srinivas sir for organizing this AICT Vani program, um, especially on quantum computing. This is the latest topics right now. Research is going to take place in this area. Lot of scope is also there. Right now, most of uh, the DST projects are going on in this area only, quantum machines and quantum algorithms. So I would like to start with quantum machine learning basics and applications. Today, here see uh, exploring revolutionary intersection where quantum physics meets artificial intelligence. Here you can see right now quantum physics is going to has a unique role. Whereas if we are going to match with artificial intelligence, then the entire scenario is going to change. The new frontier is going to open up, and it is going to change the entire quantum machine learning techniques, and this computational problem solving and classical limitations are there. So all these classical limitations, problem solving methods, earlier we are having some computational problems are there. So these problems can be overcome by this quantum physics as well as artificial intelligence. Coming to the quantum machine learning, what is quantum machine learning? Here you can see machine learning represents the groundbreaking fusion of quantum uh, computing principles with machine learning algorithms. So here the important thing is quantum phenomena like superposition and entanglement to enhance computations in the way previously thought impossible. So it is going to match whenever we are going to talk about fusion techniques, we are going to mix these two techniques like we are having two. Earlier we have discussed about quantum physics and quantum, and next one is artificial intelligence where we are going to match. So QML offers potential solutions to the problems like classical machine learning struggles with, such as complex optimization challenges we are having and processing enormous data sets with intricate patterns. Especially if you talk about image processing and speech recognition, lot of large data sets are there. Lot of enormous data is there. So how to solve such type of things is the most important thing. By using this common machine learning or regular machine learning algorithms, we can't solve some of the these complex challenges. So optimization to be done. So in by using this QML only, where we can solve such type of problems. Okay, that's the beauty of QML. Coming to the why quantum machine learning and the motivation, here you can see the classical limitations. First one is traditional machine learning faces increasing constraints in speed and scalability as data complexity grows exponentially in our digital world. So nowadays, data is going to change rapidly. So a lot of data we are going to see every day. So a lot of transmission and receiving is going to take place. So we need to study the data. We need to solve the data. If there is any redundant data is there. So such type of problems comes into the picture. So we are facing such type of problems. How to overcome that thing by using quantum machine learning? Because these classical limitations are there, general limitations are there. We are seen with the traditional methods. These problems can be overcome by using this quantum advantage. So quantum computers process multiple states simultaneously through superposition. This is the main beauty of this quantum. So generally, if the data is in either zero or one state, generally, if you are going to use our gates, we are going to use AND gate, OR gate, NOT gate, like that. We are having some of the gates are there. Whereas quantum computing, we are having different gates are there. Suppose they are proposed different types of gates here, different quantum circuits comes into the picture. So quantum computers process multiple states simultaneously, either zero or one also it's going to process. That's the beauty of this quantum. Whereas coming to the transformative potential, QML promises dramatically faster training of complex models and significantly improved pattern recognition in high dimensional spaces. So most of the time we are having training of huge data is one of the problem we are having in the machine learning. So to solve such type of things, what we are going to use QML. QML is the one way of best solution for that. What we are going to call it as classical limitations. So one is training the data sets, complex data models or data sets. Next one is improved pattern recognition in high dimensional spaces. That's the most important things. So this quantum speed up would transform industries from healthcare, finance, like that. Because in the healthcare, we a lot of patients are there. So that data is huge data comes into the picture. So there are some of the every if you see if you take any patient, there is a patient history will be there. For every year, in which month he is having this problem, if he is having any other problems are there, then we are having case history will be there. Like that, how to resolve those things by using the complex data. This is one area we are having. And coming to the finance, like if you are having demat accounts and all these things, bank accounts, huge transactions are there for each person. So that tracking also can be easily done by using this quantum machine learning. So breakthrough capabilities are there in this in the prediction and optimization. So a lot of scope is there for quantum. That's why now the paradigm has shifted from traditional machine learning algorithms to quantum machine learning algorithms. So here you can see foundations of quantum computing. We are having some qubits are there, entanglement is there, quantum gates and circuits. These are the basic things where we are going to have. So coming to the qubits, qubits that exists in superposition, either one or zero, representing both one and zero simultaneously. That is the thing where we are going to discuss. Next one is enabling exponential more information storage than the classical bits. So this is the most important thing where we have seen. Whereas coming to the entanglement, quantum phenomena where qubits become linked so that the state of one instantly influence another. So here, if we know the state of one thing, one gate, where we can predict the other gate, other quantum bits also by using this qubits entanglement. So this is the one important thing, especially in image processing, where we are going to use. If you know the state of one pixel, where we can process the remaining pixels, what is the distance between them and what is the state between them, and everything where we can calculate by using this entanglement. Whereas coming to the quantum gates and circuits, we are having operational elements are there that manipulate qubits to perform computations far beyond classical capabilities are there. By the time of quantum gates, we are going to discuss some of the traditional gates are there. Q naught gate is there, where we are having hard mod gate is there. Like that, some of the gates are there. We are going to discuss shortly, forming the building blocks for quantum algorithms. So coming to the mathematical foundations for QML, here you can see linear algebra is there. So in linear algebra, we are going to see vectors, matrices, uh, and tensor products from the mathematical language for describing quantum states and operations. Whereas coming to the Hilbert spaces, where we are having complex vector spaces are there, providing mathematical framework for representing quantum states and their transformations. So we are going to use linear algebra, Hilbert spaces, as well as quantum measurement. The probability amplitude governs how we extract classical information from quantum systems. So we are going to discuss about amplitudes also, and the position of the qubits also. So like this, some of the things where we are going to measure fundamentally different from the classical probabilities. Okay. So these are the three mathematical foundations that are required for any student to learn QML. So linear algebra, Hilbert spaces, and quantum measurements is the important things. Let us see one by one. So what are the problems we are having? So classical machine learning refresher. Here you can see learning paradigms is there, key challenges are there. Generally, we learn so many things from machine learning, that artificial intelligence and machine learning. that is supervised learning, where we are going to training with labeled examples. We are going to train, for example, the fruits are there, apples are there. Then what we are going to do, red apples are there, green apples are there. What we are going to do, all the red apples we are going to group and we are going to label as a red apples and we are going to train them. Similarly, whereas coming to the unsupervised learning, finding hidden patterns. Based upon the hidden patterns, we are going to find. Similarly, for semi-supervised, also limited labels are there with unlimited, unlabeled data. Like that, we are going to semi-supervise. Coming to the reinforcement learning, where we are having learning through environment interaction only, it is going to take place. What are the key challenges we are having is one is computational cost grows with the data complexity generally. So whenever we are going to take huge number of data sets, then we are having a problem. So how to solve this problem is these are by using this QML is one of the solution. And coming to the training time becomes prohibitive for large models. So most of the time training the large data sets is one of the problem we are facing. So how to for that we need to have a solution for that. And coming to the difficulty handling high dimensional data structure. Okay. Next one is exponential scaling problems with certain algorithms. So these are the challenges we are having. The four challenges here. One is complexity. Next one is training. Next one is training data of large models. Next one is third one is difficult handling high dimensional data structures. If we are having more than one or two the high dimensions we are having, then uh, handling such type of things is difficult, especially in this machine learning. Whereas in QML, it is easy to process that different dimensional data structures also. That's the one of the advantages we are having. That's why we are moving from traditional machine learning to QML. Coming to the exponential scaling problems also that comes into the picture. These are the challenges we are having. So the limitations, classical limitations create the opportunity for the quantum approaches to provide substantial speedups and new capabilities. Can you stop recording for once? Okay, we will continue the session. So coming to the quantum data encoding methods, we are having basic encoding is there, amplitude encoding and angle encoding. So these are the three encoding techniques we are going to use. So maps classical bits directly to qubits in computational basic states like zero state qubit and qubit 0 and qubit 1. And most straightforward but least efficient process. Basic encoding, where most of the time we are not going to use, but for basic applications we are going to use. Whereas coming to the amplitude encoding, encoding classical data into amplitudes of quantum states, enabling extremely compact representation of n-dimensional vectors like log n qubits like that. Here we are going to see. So amplitude encoding is there. Already we know how amplitude is encoding we are going to take place in the general state. Where is this encoding classical data into amplitudes of quantum states is here we are going to perform. Whereas coming to angle encoding, represent data as a rotation of angles of qubits. So, for example, qubit 0 is there. What is its rotation when you apply it to a particular gate? What is the entanglement in this case? If you apply for a hard mod gate, qubit 1, what is the superposition is going to take place, which is it may is going to represent either 0 or 1, and what is the rotation has taken place in that particular axis. Like that, we are going to take. So here, enabling flexible transformations and natural implementations of quantum operations. So we are having quantum machine learning algorithms and tools that are available. One is quantum support vector machines. We know support vector machines in machine learning. Right now, we are applying this quantum support machine vector machines as QSVM, where we are going to use. So in QSVM, we here you can see leverage quantum kernels to perform classification in higher dimensions than classical plausible. So most of the time, first thing is we need to classify that thing. Classify the thing. One is classifying how we are going to classify and how larger dimensions we are going to perform. Both the things can be done by using this QSVM, quantum support vector machines. So these which are going to offering at high speeds, we are going to perform. That is the beauty of QSVM. Whereas coming to the uh, variational quantum circuits here, trainable quantum circuits analogous to neural networks. Next one is enabling quantum versions to deep learning with fewer parameters are there. Okay. So these are the neural networks where we are going to use for quantum variational quantum circuits. Next one is QML frameworks, quantum machine learning frameworks are already that are available in the market. One is PennyLane, TensorFlow, Quantum, and QCIT enable hybrid quantum classical workflows. Next one is bridging current hardware limitations. So these are the QML frameworks we are having. Depending upon the type of application we are going to choose, we are going to select that frameworks. Coming to the real world applications like QML, here we can see lot of areas are there in there because if you talk about drug discovery, see here you can see simulating molecular interaction and protein folding at unprecedented speeds, potentially reducing pharmaceutical development timelines from years to months. So molecule interactions are going to take and from protein folding, these are the unprecedented speeds where we need to perform by using this QML because it will take years to perform to get an output in the drug discovery. So we can speed up that process by using this QML techniques and especially in the drug discovery area so that we can get the results in the months itself. So where we hear the speed up of entire process is going to take place where we can discover new drugs also which are useful to the human beings. So there's a lot of applications are there. That's why people are interested to do research and the working in this QML areas. So they are going to solve some of the problems in the real world problems. Whereas coming to the financial modeling, portfolio optimization using quantum approximate algorithm optimization algorithms are there. That is nothing but QAOA, and to find optimal asset allocations beyond classical capabilities. Because most of the time, whenever we are going to have a financial modeling, because we are having huge data sets comes into the picture. If you talk about what do you call every year we are going to perform uh, income tax. So if you take a state, a huge number of taxpayers are there. If coming to entire country, we are having quantum. If we apply this quantum machine learning, how the person is going to, we can track the particular banking sector of a particular person, where we can entire things can be assets allegation, everything we can track, and we can do this financial modeling in a better way. So, whereas coming to the image and speech recognition, and till now we have discussed in different domains like drug discovery, financial modeling, image and speech recognition. But especially for EC department, we are from the EC department. So in EC department, we are having a lot of scope is there in image and speech and recognition. Here, enhanced classification with quantum enhanced algorithms. Next one is potentially enable real-time processing of complex multimedia data. That is the most important thing. So in image and speech cases, for example, if you take a horticulture university or a agriculture university, because for each crop, there are a lot of images are there. So different types of insects are that are going to affect the field. So how these fruit flies are affecting the particular crop and what type of pesticides we need to use and what is the state of the leaf and what are the problems in that, like that we are going to discuss. So these are we are having huge data sets that comes into the picture. Applying this huge data set to the normal machine learning process is going to take much more time. Try we are having training is there, testing is there. So modeling that thing is one of the most important thing. If you are having a huge data set, then it is going to take more time to run that thing. So all these things are the challenges we are having. So these challenges can be overcome by this quantum machine learning. So here you can see quantum classifications with quantum enhanced algorithms are there. That's potentially enabling the real-time processing of complex multimedia data. Similarly, in the speech processing also, we are having different algorithms that are there. But where we are having if you are having huge data set is there, for example, if you want to recognize a particular person's voice in out of the database, if you are having huge data set is there. But if you are going to use common machine learning algorithms, it is going to take more time. Whereas if you take with the uh, QML, quantum machine learning, if you apply this QML to the speech recognition thing, out of this, if you are having huge data sets like um, is also there, then in that case also it is going to identify very quickly, so that where we can perform um, in a better way with the when compared with the classical algorithms. So coming to the logistics and the supply chain, solving complex routing and resource allocation problems that intractable for classical computers due to combinatorial explosion. So here you can see some of the classic we are having some of the resource algorithms. So in this case, where we can talk about Amazon or some other logistic services, which are right now most of the time we are going to use these classical problems where we are seeing every day. But the thing is, we are resource allocation is the problem, and where we are how we are going to perform these tasks is in the routine way is the some of the problems. These problems can be overcome simply by using this QML. That's why we are going to use for logistics and supply chain also. So these are challenges and limitations and the road ahead we are having. So current limitations and future directions here you can see limited qubit counters are there. That is 1000 currently nearly available. Whereas higher noise and error rates in quantum operations and short coherences times restricting computation depth also need for extra extreme cooling and isolation from environment. This is the one important thing we are having. That is one of the limitations we are having. So these are the current limitations we are having. So we can overcome these current limitations in the future time, where we can overcome these shortfalls, where we can move ahead and we can give a better direction for that. Whereas we are coming to the future directions, here you can see development of fault tolerant quantum computers are there, and improvement of hybrid quantum classical algorithms are there, quantum error detection and at scale. Next one is industry specific QML applications and standards are there. So quantum advantages for machine learning remains largely theoretically today, but rapid hardware advances are going to take place. Practical implementations are within the next decade. Right now, DST projects are coming very all the every college they are asking you uh, to apply. But the here, if you are going to apply, we need some we need to have reliable vendors for that, because 75% they are going to provide from the DST side, and 25% we need to keep from our college end. So right now, DST proposals are running. Every college, every university is applying for DST in this domain. So a lot of scope is there up to 2031 where we need to run these projects. So we need to have IBM or TCS connections will be there. Then we can apply for that. So hope to you understand today's class, and thank you for giving this wonderful opportunity. I would like to thank Dr. Bachu Srinivas sir for giving this excellent opportunity to me, and I would like to thank your management. Especially department EC, EC department HOD and staff, students. Thank you for your wonderful support. Hope you can continue this type of legacy in the future also. Thank you one and all for giving this wonderful opportunity. Hope you can understand this thing. Thank you one and all. Bye.